All righty, look at that. Good morning, lads and ladies. Welcome back to College Algebra. Today is a fun day indeed. I'm glad to see so many folks here. We are going to start learning about logarithms today. And logarithms represent a kind of spike in difficulty for us a little bit, because we're going to be combining the objects we've just been studying, exponential functions, with the thing we were studying right before then, which is the concept of an inverse function. So you might deduce that logarithms are the inverses to exponential functions. That's the story. And I could just stop there and say, hey, now you figure out all the rest of this shit for yourself, but that would be horribly cruel, because it turns out the algebra of these things is somewhat complicated, and they are a little bit hard to work with. So we're going to introduce this gently. This whole week will be 2 homework assignments. And then next week we'll have 1 homework assignment and 1 quiz, and that will lead us up into the 3rd test. So that's kind of our roadmap. I think that's enough of me babbling. So let's go ahead and talk about some mathematics. No, go away. All right. Oh no, my wife stole my good black pen. She might have done. Let's see how this works. Yeah, she might have done. And today's the 6th. I do think I'm gonna have to hunt for another pen. Sorry, guys. Okay. That's better. All right. So today we're going to introduce logarithms. Ooh, focus. There we go. Okay. And to give you a quick look, the homework set up for this week. Here. So you should be done with everything up through quiz 6, right? Quiz 6 and the previous 3 homeworks are due today at the start of class. If you do need more time on those, as always, you can send me an email and I can extend them for you. There's no penalty for that, and I would much rather you finish them than not, because it's important practice for the test. But the 2 new things for this week are homeworks 19 and 20. Those will be due next Tuesday. And then there is 1 more homework set dealing with logarithms and exponentials, which I will give you next week along with quiz 7. And then we will be doing exam 3. And then the last little bit of material for the class after that is a discussion of systems. And exam 4 is really just going to be about systems. It's very simple. But this section, the section on logarithms, is not so simple. So see, is there anything else we want to say? Not really. Let's get into it. As with all new topics in mathematics, we need to start with the definition. Let's see. So the base A logarithm is the inverse to the function, I should say to the base A exponential function. That's probably the cleanest way to say it. I'm going to give you several other equivalent definitions. This one is good conceptually, and it does do the job, but it doesn't really tell you how the algebra works. But this is the most common one. So we'll say That is, if f of x is just a to the x, then f inverse of x is this new thing called log subscript a of x. This is the logarithm. All right, and this is the definition. An alternate way of saying this could be expressed by taking the definition of the inverse function, right? That you compose one with the other and you get the identity, or that it sends outputs back to inputs. Each of those will have an algebraic characterization, and I will give you those algebraic characterizations in time. But I want you to write this down and hold on to this as our kind of first definition, because it really is the thing that ties together the concepts we have from the past with the place we're going in the future. So let me try to motivate this. In your homework, you've noticed that some of the problems ask you to solve an exponential equation. Like there was a problem with birds, right? And you had to say when the bird population reached 48,000 or something like that. And the function that modeled the population for the birds was a polynomial function, not a polynomial, it was an exponential function. So you ended up with an equation that looked like, an exponential function equals some constant. And you had to try to solve for x, which was a little bit tricky. So let me say it like this. Consider the equations 2 to the x equals 16. 3 to the x equals, let's say, 1/9. And 5 to the x equals 25. And 2 to the x equals 3. Because really, while it's true that logarithms are the inverses to exponential functions, the utility of those things comes in equation solving largely. That's at least at our level. Now, these first few equations, I bet you could figure out how to solve if you took your time. Who could help me figure out the solution to this equation? 2 to the x, okay, so this is an exponential function. The base is 2. I want to know, when is 2 to the x equal to 16? So anybody, just tell me what you would do. Imagine this is the test and you have no guidance. What would you do to try and start solving this equation? Any thoughts are welcome here. No romance. Yeah, I like what Justine says. I mean, it's not normally how I would like to solve equations, but it sure as shit, if you got no idea what else to do, plug in some numbers for x, right? All right, what happens if I plug in x equals 1? Well, then I get 2 to the 1 equals 16. That's 2 equals 16. That's not true. If I plug in x equals 2, I get 2 to the 2 equals 16. Well, 2 to the 2 is 4. That's not 16. If I plug in x equals 3, let me write some of these down. So when x is equal to 3, we get 2 to the 3 equals 16, which is the same as saying 8 equals 16. That's not true. But when we get to x equals 4, we get 2 to the 4 equals 16. And 2 to the 4 is 16. This says 16 equals 16. So, yay. X equals 4 is the solution. So this first one is fairly straightforward, and you could solve this one in that same manner. What about this next guy here? -3 is a reasonable guess. It doesn't turn out to be quite correct here, but you're close. A way of solving this that is a little bit more careful, you can kind of take inspiration from what we saw as we plugged things in here. If I can rewrite 1/9 as a power of 3, that would be dope, right? That would do the job here. So the left-hand side is still 3 to the x, but 1/9 is 1/3 squared, right? Because 9 is 3 squared. And then 1/something, that's the same as that thing to the -1. So I could say this is 3 to the x equals 3 to the -2. Right? 1/3 squared is 3 to the -2. And now I can say, oh, okay, x has to be -2. Do you guys follow that? So I'm going to rewrite this equation in several different forms, hoping to make it easier to solve. 1/9, well, I know that 9 is 3 squared. So I rewrite this equation as 3 to the x equals 1/3 squared. The 1/, is the 1 from the 1/9 here, and I'm just rewriting 9 as 3 squared. So I get this equation. And then I start thinking, well, oh, okay, so I've got 3 to the x on the left, and I've got 1/3 to the 2 on the right. If I could make this look more like this, then maybe the powers would be equal. So let's see. Okay, yeah, 1/3 squared, that's 3 to the -2. And then if I've got 3 to the x equals 3 to the -2, it follows that x is -2, right? The only way for 2 powers of 3 to be the same is if the powers are the same. In fact, we're using something here called the one-to-one property. Remember we talked about one-to-one functions? We're using the fact that 3 to the x is a one-to-one function when we go from here to here. If I use that same logic on this guy, (25), that's 5 squared. So this is 5 to the x equals 5 to the 2, right? 5 to the x is 5 to the x, and 25 is 5 to the 2. And so right away here, I get that x is equal to +2. But when I get to this guy, I can't write, let's see, can't write 3 as a nice power of 2. Which appears to be frustrating, right? I can't do the shit that I was doing on these last two. So each of these last two was pretty easy to solve because I could turn the right-hand side into that base, the base that was on the left. Here I could turn 25 into a base 5 expression. But here I run into trouble because there's no obvious way to write 3 as like 2 squared or 2 cubed or anything. And in fact, if you start trying to plug in numbers, if you plug in x equals 0, you get 2 to the 0 equals 3, which is the same as saying, well, 2 to the 0 is 1. This is the same as saying 1 equals 3. That's no good. Right, just like this was no good. This is no good. If I plug in x equals 1, I get 2 to the 1 equals 3, which is the same as saying 2 equals 3. That's also no bueno. Something weird happens here, though. If I plug in x equals 2, then I get 2 to the 2 equals 3. So I go from being too small to too big. 2 to the 2 is 4. So this is no good. So what gives? Is there no solution to this bottom equation? That becomes the question. If there isn't a solution, why not? And if there is a solution, how do I find it? It looks like there isn't a whole number solution, right? 0 and 1 are definitely too small because those lead to numbers that are less than 3. But 2 looks like 2 is too big. That leads to a number that's larger than 3. So I want to look a little bit more closely at that bottom equation. And I want to think about it in terms of a graph. Let me consider the two curves, y equals 2 to the x and y equals 3. Two to the x is a growing exponential. We've looked at that graph before. It was one of the first ones we looked at. It's got to be all the way up here at like 8, which is pretty much off my chart. Okay. So here's the graph of 2 to the x. And the graph of the function y equals 3 right here. So does the equation 2 to the x equals 3 have a solution? What can we say from the graph? What would a solution to this equation look like in terms of this graph? Very good. It's where the graphs hit one another. It's the x value where these two graphs touch. This x value right here is the solution to the equation 2 to the x equals 3. So what is that number? Oh, let's take a look. I can hit y equals up here. I'm going to graph something. Then I type 2 raised to the power of x. And then for y2, I type in just 3. I can play with my window settings a little bit to kind of make things match here. My window settings are going from like -3 to 3 along the x-axis. And the y-axis, I'll say from like -1 to 10. That's about the picture I'd found there. Okay, so here's 2 to the x, here's 3. If I take this trace tool and I walk my cursor as close as I possibly can to that number, this y value looks, or sorry, this x value, 1.65, there we're at 3.15, that's a little too big. If we come back just a teeny bit, there we go, that's better. 1.595. Maybe if I come back a little further, that's too small enough. So somewhere around 1.5, like 1.58, 1.59, somewhere around there. So this looks to be, from the graphing calculator, this appears to be about x equals, say, 1.58. And indeed, if we come back here and I type 2 raised to the power of 1.58, I should get something really close to 3. Yeah, look at that, 2.989, very, very, very close to 3. But what is the exact solution? So saying here, and indeed, 2 raised to the 1.58 is equal to 2.989, blah, blah, blah. Very, very close to 3. But what is the exact solution? Well, the exact number there the exact solution to the equation 2 to the x equals 3 is the number x equals log sub 2 of 3. Oh, sorry, the calculator's in the way there, isn't it? This is the exact number. And it's called the base log 2 log of 3. Log base 2 of 3. And there is a way to enter arbitrary base logarithms in this calculator. Although I'm so used to using the change of base formula, there it is. I can type log base 2 of 3. And you see I get 1.58496250. Now that is still just an approximation. The exact solution is log base 2 of 3. So we have a pretty good guess here. But this is the exact solution, right? Actually, this right here, the base 2 log of 3, that is the exact solution. And this is why logarithms are so powerful. I'll show you in a second, Brooke, and it's actually kind of unfortunate. You can only do that on the 84. You can't do that on the 83. So I'm going to show you a way to do it in the old calculators and in the newer calculators. There's a tool called the change of base formula. And then the newer calculators, the 84s, not that they're new, but those have a specific thing to do with logs of arbitrary bases. So this leads us to our kind of second definition, which is our more useful definition. Says for any positive number a, our numbers a and say y, a to the x equals y means the same thing as x equals log base a of y. And I think this is the definition that most people find maximally useful. There is one more, and they are all equivalent. The number a has to be positive because it's the base of an exponential. And remember, bases of exponentials, the exponential function only makes sense if its base is positive. The number y has to be positive because the output from exponentials are always positive numbers. Right? Every exponential graph has this property that it never sinks below the x-axis. We talked about the range of exponential functions way back when we first introduced them. So if your goal is to solve an exponential equation, then the trick is to simplify it to something like 2 to the x equals 3. Some number to the x equals some other number. Then you can rewrite an expression like this as an expression like this. And what I want to do before I show you any other tricks in the calculator is just go back to those first few examples, the ones that we could solve just kind of by thinking about them, and see if we can state them in logarithmic form. And this will be the main tool. So make sure you have this somewhere nice and clear in your notes. For most of the homework this week, this is going to be your primary tool. If you're asked to simplify a log expression, you need to think about it like this. If you're asked to solve an equation like this, you will write it like that. Okay. So let's return back to these first few guys. I'll rewrite them. Previously, we said that 2 to the x equals 16 means x equals 4. Oh, this is a bad one. We also said 3 to the x equals 1/9 means x equals -2, and 5 to the x equals 25 means x equals +2. Let's rewrite each of these. In logarithmic form. Okay, so I'll label these as A, B, and C. A, 2 to the x equals 16. Think about that statement, that alternate definition of the logarithm I just gave you. this means x is equal to the base 2 logarithm of 16. And we already know the solution here. We know that the solution of this equation is x equals 4. So the base 2 logarithm of 16 is equal to 4. It is. And similarly, 3 to the x equals 1/9. If I want to rewrite this exponential as a logarithm statement, again, we're using this blue box alternate definition here. This guy. 3 to the x equals 1/9 would mean x is equal to the log base 3 of 1/9. And then we can infer, because we know the solution to this is -2, that the base 3 log of 1/9 has to be 2. And then finally, 5 to the x equals 25 could be rewritten in logarithmic form as x equals the base 5 log of 25. So the base 5 log of 25, oops, sorry, this is a -2, is equal to 2. Yeah, this is -2. This is positive. So logarithms allow us to rewrite things like this. And if you know the solution to the thing like this, then you can say what that log is equal to. I'm gonna get us some more practice, just computing logs here. I'll take them from your homework. We'll take 1 or 2 from your homework. Oh, you're not gonna work now? No, I'm trying. We'll close the quick window to actually start coding. Oh. Oh, there's some notation. They jumped right in with that notation, huh? Yeah, okay. I guess I have to introduce a little bit more notation before we're ready for this. So let me go ahead and do that. Some special notation. There are 2 logs that we use more than others. Too frequently used logs. The base 10 logarithm, the base 10 log of x or whatever. Just like with the square root and cube root and fourth root and fifth root. With the square root, you don't write the 2, but with the cube root, fourth root, fifth root, you do write the numbers. Well, with the base 10 logarithm, you don't write the base. So if you see just log of something without a base, that means it's the base 10 logarithm. This is called the common logarithm. Common because our number system is the base 10 number system. And essentially, if you take the log of a number, it'll give you the number of digits, right? So the log of 10, I should say, it gives you one less than the number of digits. The log of 10 is 1. The log of 100 is 2. The log of 1000 is 3, and so on. Common log, and that's a log without a number written down here. That always means that there is a number there, it's a 10, right? We just don't write it the same way we don't write the 2 for the square root. The other one you're going to see a lot is an abbreviation for the base E log. And remember, E is that special number we met at the end of last week, called the natural base or Euler's number, the 2.718. This is called the natural log, or ln. That number E shows up surprisingly often in nature. It shows up in lots of places you really wouldn't expect it to show up. And so much so that people refer to it as the natural base. It's the base from nature. And that terminology is used both in terms of the exponential. You talk about the natural exponential. People are talking about e to the x. And when you talk about the natural logarithm, people are talking about the base e log of x. Okay, so these 2 bits of notation, these are what we need in order to look at a handful of problems like this. So let's do it. Yeah, here we can take just a few of these. Let's evaluate the log of let's say 10,000. The log of over 100, and the log of the square root of 10. We'll also evaluate the ln of e to the 8, the ln of 1. And while we're here, let's do a few others. How about the 7 log of 49, and the base 3 log of 1 over 81. Plenty of practice here. The trick to evaluating each of these is to think about them as an exponential statement. So for each of them, I'll just go ahead and call this thing x, and that will give me something to play with. Now, hearken back to that alternate definition. If x is equal to the log of 10,000, what must be true? First, what's the base here? I don't have anything written for these first 3. So what is the base for all 3 of those? Very good, 10. All right, if there's no base written, the base is always 10. Alrighty, so how could I rewrite this as an exponential statement? How can I rewrite this without a logarithm? What is the equivalent statement here? Think of this. Yeah, very good. Right? So x is equal to the log base 10 of 10,000 is the same thing as saying 10 to the x is equal to 10,000. All right. So then what is x? Remember, that's what I'm trying to find. So I rewrite it like this, and then I try to figure out what is x that makes this true. What power of 10 is equal to 10,000? Four. Yeah, very good, right? 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, 10 to the 4 is 10,000. So x equals 10. I'm sorry, to x equals 4, i.e. the common log of 10,000 is equal to 4. You guys follow what's going on there? We'll get faster and faster at this. Before we try to find any shortcuts, let's jump down to the second one and see what we can do here. So again, I'll call it x. That gives me something to work with. I rewrite this as an exponential statement. X equals the common log of 1 over 100 is the same as saying 10 to the x is equal to 1 over 100. So what power of 10 gives me 1 over 100? Very good, -2, right? 10 to the 2 is 100, so 10 to the -2 is the reciprocal of 100. So x has to be equal to 2, x has to be equal to -2 here, i.e., or that is, the common log of 1 over 100 is equal to -2. Now we can start to do this faster if we think about it. What are we saying here? I'm saying 10 raised to what power gives me the thing inside? So what power of 10 gives me the square root of 10? To what power must I raise the base 10 in order to get the inside here, the square root of 10? Very good, 1/2. So if we want to, we can say this is just equal to 1/2 because 10 to the 1/2 is equal to the square root of 10. And we could have made a similarly quick argument for all of the previous guys. So rather than going through these intermediate steps, we can just kind of jump to the answer if we understand what the question is. Same sort of thing here. What's my base for the natural logarithm? So the ln of e to the 8. What is the base of that logarithm? E. Good. So here we're asking what power of e, right? What power of this base, what power of e gives me e to the 8? Don't think too hard about that one. To what power must I raise e in order to get e to the 8? Yeah, exactly, 8. These sort of things for natural logs often look a little bit silly. But if we call this x, then we would get e to the x equals e to the 8 for the statements like this. So yeah, clearly it's equal to 8. Oh, that's awful. All right, this next one's a little bit fun. To what power must I raise e in order to get 1 out? Good, 0. So the natural log of 1 is 0 because e to the 0 is equal to 1. All right, let's try these last couple. The base 7 log of 49. To what power must I raise 7 in order to get 49? Very good, 2. Because 7 to the 2 is 49. Okay, last one here. To what power must I raise 3 in order to get 1 over 81? Very good, -4. 3 squared is 9. 3 cubed is 27. 3 to the 4 is 81. So 3 to the -4 is 1 over 81. Okay. So most of the time you'll make an argument like these, right? You should be getting comfy with these. But if you're ever stuck, you can always call the thing x and then rewrite it as an exponential statement and try to figure it out from there. Because that's really what we're doing in our heads every time we do this. I want to talk now about the logarithm as a function. Share with you some of the important properties of the logarithm function. So it is a tool for solving equations. That's where most of its utility comes from, especially at the college algebra level. But it's also a function in its own right. What do you notice about these outputs? Well, sometimes they're positive and kind of big numbers. Sometimes they're positive and kind of small numbers. Sometimes they're 0. Sometimes they're negative. So the range of a logarithm function, these are all different functions, different bases, but the range of a logarithm function could be any real number. Let me take a specific example here. Let's look at the base 2 logarithm. Draw its graph. And we'll do it the old-fashioned way. We're just going to plot some points. I'm going to choose these inputs carefully. All right, I'm choosing these all to be neat powers of 2 because I want the outputs from this function to be nice. And remember what the log base 2 function does. It tells you what power you have to raise 2 to in order to get the input. It's the inverse of the base 2 exponential. So what is the base 2 log of 1/4? To what power must I raise 2 in order to get 1/4 out? Very good, -2. All right, what is the base 2 log of 1/2? To what power must I raise 2 in order to get out 1/2? Kendra, Logan, Brooke? Yeah, Matthew, thank you, -1. All right, what is the base 2 log of 1? To what power must I raise 2 in order to get 1 out? Excellent, 0. The base 2 log of 2? That would be 1. The base 2 log of 4, thank you. Oops, sorry, base 2 log of 4. That is 2. And the base 2 log of 8? Yeah, this one is 3. So I can plot these points. Mark this as like 1, 2, 3, 4. Might not have room to get out to 8. Yeah, I don't. We'll say 5. We'll stop there. So this line right here tells me that the point 1/4, comma, -2 is on my graph. So I come down to 1/4 is like right here. All right, if this is 1, 2, 3, 4, 5. 1/4 is a quarter of the way to 1. So 1/4, comma, -2 right here. And then 1/2, comma, -1. That's like right here. 1, comma, 0. Right here. 2, comma, 1. 2, 3. So yeah, 2 comma 1 is next here. And then 4 comma 2, that's the last guy I'm going to actually have room to put on the graph. It's right here. 1/8 would be like right here. And 1/8 would correspond to the output -3. So he would be like right over here. So what's going on is we have actually a vertical asymptote here at 0. And then we grow as we go off to this direction, off to the right. And that growth is quite slow. Looking something like this. This is the graph of the base 2 logarithm of x. This is the graph of this function. And if you want to understand why we have a vertical asymptote here, it's easiest if you think about it in terms of that first definition. This is the inverse of the base 2 exponential, which you know has a horizontal asymptote over here, right? The base 2 exponential has this sort of looking graph. And we know that if you reflect the graph over the line y equals x, you get the graph of its inverse. So let me state a few things. The domain is the open interval from 0 to infinity. And this is the same for all logs. Same for all functions like f of x equals log base a of x, regardless of the number a. The range is all real numbers from -infinity to +infinity. It goes down as far as you want here, and it goes up as far as you want here. It just takes a long time to get there. And this is also the same for all functions of the form f of x equals log base a of x. And again, another way to see this is that the range of an exponential is 0 to infinity. And the domain of an exponential is -infinity to infinity. These are the inverses, remember, of exponential functions. So the domains and ranges switch. This is something we learned back in section 4.9. All the basic logarithms have the same shape graph. They all have the same vertical asymptote. It's the line x equals 0, and it's always approached like this from the right. I'd like to show you another example quickly in Desmos, where we can draw both the logarithm graph and the exponential graph. All right, so here is, for example, log base 2 of x. And here's 2 to the x. And you see they have this symmetry. They are symmetric about the line y equals x. Y equals x. So the blue is 2 to the x, and the red is the log base 2 of x. And if you take any point here and you flip it over that line, you get a point here. Like 2 comma 4 is on 2 to the x, so 4 comma 2 is on base 2 log of x. 3 comma 8. It doesn't want to pick it out. 3 comma 8 is on 2 to the x, so 8 comma 3 is on the base 2 log of x. It's this red graph that we just sketched. All right, and you see the vertical asymptote here diving down, and you see it increases as we go off to the right. I could change the base to other numbers. Like I could change this base to e and change this to e, and you get that same symmetry. So all the logarithm graphs kind of look like this, just like all the exponential graphs kind of look like this blue. This is an important thing to remember. So you need to know both of these graphs. The new one is the logarithm graph. And I want to point out one particular hazard here. Notice this never actually hits the y-axis. If I zoom in really, really close, you'll see there's always a little bit of space. It never actually hits that. Even if it looks like it does, if you zoom in enough, you see there's a little bitty gap. And it'll get real, real close, but it never hits. And it goes down and down and down and down and down and down and down forever. All right, that's what we mean to say we have a vertical asymptote there. Now, if you draw this graph on your graphing calculator, let me draw the same graph here. This one was, the red one right now is the base e logarithm, which is ln of x. Play with my window settings a little bit. We'll just do the normal thing, -10 to 10. If I graph this here, it looks like it has a y-intercept, doesn't it? But it really doesn't. That's bullshit. That's just the resolution of that calculator biting you in the ass again. We've seen this a few times before. So this might look like it's a y-intercept here, and the curve just starts right there. But that's not true. All right, if you look on Desmos or you look on a more powerful graphing utility, you see that this goes down and down and down and down forever. So if I ever ask you to draw the graph of a logarithm, or I ever ask you, does a logarithm's graph have a y-intercept? What's the answer? Yeah, it does not have a y-intercept. Thank you. All right. So coming back over here, if you need to draw a graph of a log by hand, this is what they look like. It is something that I'll be asking you guys to do at some point, so please be aware. Other stuff for this level right now, not a whole lot more. We can get some more practice solving equations. You know, we can evaluate things like this by hand. It's not too bad. Let's see, do we need any of these other properties yet? Range domain. We've done these. Yeah, change of base formula. Okay, yeah, so we will need to talk about that. Let me show you the change of base formula, and then we will do a few more problems. You saw how the two red graphs there, the base 2 log and the natural log, looked very, very similar to each other. There wasn't a big difference. Indeed, all of these different base logarithms are constant multiples of each other. So here's the change of base formula. This is how you enter other base logarithms in your calculator. Suppose somebody gives you the base b log of x but you really want to base A logarithm. All right, maybe you don't have a base B log button on your calculator. You can rewrite this as the base A log of x divided by the base A log of B. So if somebody gives you a log in a base that you don't like, you can change the base like this. Two special cases of which if you want to change from like an arbitrary base logarithm, like a base 2 logarithm, into a natural log, you just take the ln of the inside and divide by the ln of the base. And that will give you the same thing as if you take the common log of the inside and divide by the common log of the base. So earlier when I used that base function on the calculator, the question was brought up, how did you do that? And the TI-84 does have an arbitrary base program or mechanic. But if I wanted to evaluate, let's say, the base 3 log of 7 as natural logs, or the base 2 log of 5. According to the change of base formula, if I want to rewrite this as a natural log, it would be the ln of 7 over the ln of 3. And now I will show you how to do this in the calculator. A word of warning, don't try to cancel shit with logs. Just don't do it. Just don't do it. The ln's don't cancel, the numbers don't cancel, the numbers don't combine, the ln's don't combine. There are some very specific rules for how you can combine or play with logarithms using algebra. At this stage, don't do any of that shit. That's what we're going to talk about next week. That's what we're going to be worrying about down the road. And it's so easy to make mistakes. So remember, this is function notation. This is not multiplication. This is not ln times 7 or anything like that. And you can't cancel any of this stuff. It just doesn't work. But here we go. So if I want to evaluate this, I can type ln 7, close parentheses, divided by ln 3, close parentheses. And this will give me 1.7712, blah, blah, blah. Now, if you have a TI-84 or a newer, TI calculator, graphing calculator, and you hit the math button, you can scroll down to the log base here, log base. And I could enter this directly as the log base 3 of 7. And it'll give me the same thing. See? If you have a TI-83 or an older calculator, you need to use the change of base formula. The only way to enter this in your calculator is like this. Or you could use some other, you could use the LOG button, because you have ln and LOG buttons, but you don't have the other log base options. Similarly here, if I wanted to find the base 2 log of 5, I could write that as ln of 5 over ln of 2. I expect this number to be a little bit bigger than 2 because 2 squared is 4, but a little bit smaller than 3 because 2 cubed is 8. In fact, it should be closer to 2 than it is to 3. Let's see. If I take the ln of 5 and I divide by the ln of 2. Oh, I lost my divide. Divide by. Divide by. the ln of 2. We get 2.321, 2.3219. And again, if you have the fancier calculator, you could go here to math, scroll down to log base, hit enter, and then ask it straight up for the base 2 logarithm of 5. And you get the exact same thing. So if I raise 3 to the power 1.7712, what should I get? Check for understanding here. If I take the number 3 and I raise it to this power 1.7712, what should I get according to this statement here? Yeah, I should get 7, or at least something very, very close to 7. Boom, 6.999. Similarly, if I take 2 and I raise it to the power of 2.3219, I should get something very close to 5, and I do. So these logarithms, on the one hand, they're tools for solving equations. They let us solve exponential equations that would otherwise be very, very hard to solve. On the other hand, they're functions in their own right, and we need to learn how to study them like that. I think this is about all we have time for. I think we are just about out of time, and that wraps up beautifully. So the last thing I want to say is just be careful with these things. Logarithms are not magically difficult. I think it's mostly a notation challenge, and there are some tempting algebra operations, like want to cancel or combine, want to split up, want to do things with logs that you just can't do. So you need to follow your order of operations. Remember, a logarithm is like an exponent, right? It literally is an exponent. The base 3 log of 7 is the exponent to which you must raise 3 in order to get 7. So it's right there at the start of your order of operations. Right? You could think of your PEMDAS, you could insert an L after the E. It could be PELMDAS, parentheses, exponents, logarithms, multiplication, blah, blah, blah. So show them the respect they deserve. Don't try to split them up or play with them. I'll show you how to do that down the road. There are some rules, but it's easy to get those rules wrong. So please just follow the assignment and work things as they are presented here. If you do run into any sort of trouble, don't hesitate to come by office hours. I'm happy to help. Remember, to solve equations like these, you need to first rewrite them as like some number to the x equals some other number. That's all I have for you guys today. We will talk more about this on Thursday, and that's it. Yeah, so take a look at that new homework. Please get working on it. It's not too bad. If you practice between now and Thursday, it will be a big help when it comes to Thursday's lecture. All right, again, take care. Have a good day.